In this video, we start looking at what's called integral calculus. We get away from derivatives and start working towards integrals. And a vital part of that is understanding areas underneath curves. So in this video, we're going to be approximating areas under curves using rectangles. But before we do, I'm going to show you how I'm going to use my calculator to help me as we work through the algebra in this video. Now I want to show you how to use functions, especially for the purpose in this video, on a TI-36X Pro. And the way you're going to start is you're going to hit the table button here, and that's the best way I found to use functions. You get two options on the table function. Go to edit function. You can hit the number 2, or you can use your down arrow and then hit enter. And I've already got one typed here, but I'll type a different one. The function we're going to use in this video, let me clear this one, is x squared minus 2x plus 3. And so I need my x button, my squared button, minus 2x plus 3. So I've got it typed, and now I'll hit enter to store it. If I were going to actually create a table of inputs and outputs, I would set this up, but I'm not going to, so I'm just going to hit quit. So I'll hit second and mode to quit. So now that function is stored in my calculator. Now if I want to calculate the output of that function for different inputs, I can go back to my table menu and choose option 1 this time for the f of option. And now I can put in any input that I want. So if I want f of 6, I can type 6, close my parentheses, and hit enter, and it gives me the output of that function when x is 6. I could also enter, so I'll hit table again, choose f of, and I can enter a fraction as my input. So I could do like 2 over 13. Let's see, delete 2 over 13, right arrow, close my parentheses, and hit enter. And you can see you can enter whatever input you want with that function now. So this is a good tool if you're going to be inputting numbers into the same function over and over again. Okay, so back to the calculus. What we're going to do in this problem, we're going to work through the same problem in 3 different ways. Okay, so let's write down the problem. Approximate the area under the curve. Approximate the area under the curve, f of x equals x squared minus 2x plus 3 from x equals 1 to x equals 3 using, so we're approximating under the curve from x equals 1 to x equals 3 using 6 rectangles. And so we're going to work this problem in 3 different ways. The first way we're going to work it is with left endpoints. So we'll look at right endpoints and midpoints also. In all cases, we'll be using 6 rectangles, okay? So the first thing we'll do is we'll sort of sketch the graph of this curve, which is a parabola. This is a quadratic function. We're going to graph it from x equals 1 to x equals 3, but we might graph more than that just so we can kind of see the parabola play out here. So let's set it up. Let's use a marker that works. There we go. So here's 0, 1, 2, 3, and so on. So if we plug in 0 for x, the y value is 3. So if we plug in 0 for x, the y value is 3, which is up here. If we plug in 1 for x, we get negative 1 plus 3, which is 2. If we plug in 2 for x, we get 4 minus 4, which is 0, plus 3. So we can already see, because of the symmetry here, this point at 1, 2 is the vertex of this parabola. It opens upward, so we kind of know what to expect now. If x is 3, we get 9 minus 6, which is 3, plus 3 is 6. So let's see, 4, 5, 6. So 3 6s up here approximately. Graph paper is not essential here. This is a rough sketch. Okay, a very rough sketch, as you can see. But we've got our curve here, and we're only interested in from 1 to 3 now. So I'm going to cut off the rest of this, and we're going to focus on that portion of the curve. And so this is the function y equals x squared minus 2x plus 3. Now, when we say that we want to approximate the area under the curve, what we really mean is the area from the curve down to the x-axis. Okay, so some books might say approximate the area between the curve and the x-axis. Some might say under the curve. I said under the curve here just to keep the writing to a minimum. Okay, but it all means the same thing. Now, just some minor details. If the area is above the x-axis, we'll consider that to be a positive area. And if the area is below the x-axis, well, that's a negative area, if you will. Okay? In this problem, everything is above, and so everything's positive. Now, the next part to this is we need to create 6 rectangles under this curve, or using this curve down to the x-axis, from x equals 1 to x equals 3. So the way we do that is we look at our interval from 1 to 3. We look at this interval, which is the width of this interval is 2 from 1 to 3. And we need to divide that into 6 equal rectangles. So we're going to divide this by 6. And we can see that the width of each rectangle, we're going to stack 6 rectangles side by side here. The base of those, or the width of those, is all going to be 1/3 of a unit. Okay, so 1/3 of a unit. This rectangle width is often called delta x, so capital delta x. And all that means is change in x, and it's consistently 1/3 all the way across. So we're using 6 equally wide rectangles, all 1/3 of a unit wide. So the next thing I'm going to do is I'm going to set up the bases of my 6 rectangles. And so I need to measure in thirds from 1 to 3. So if I add a third to 1, I get 4 thirds. Add another third and I get 5 thirds. Add another third and I get 6 thirds, which is 2. And then I get 7 thirds, 8 thirds, and 9 thirds, which is 3. So I've got the x values for my 6 rectangles at the bottom. So I've gone from x equals 1 to x equals 3. I've got the curve. I've got the bases of my 6 rectangles. Now to finish my rectangles, I have to use what are called left endpoints. So what that means is now I need to measure the height of each of my rectangles. Okay, so the way to think about this is with left endpoints, each of these intervals has a left side. So the left side of the first interval from 1 to 4 thirds, the left side is at 1. So when I draw my rectangle in this first interval, the top of my rectangle is going to hit the curve at x equals 1. So this is going to be the top of my first rectangle. And then I draw a horizontal top and I connect from 4 thirds up. So you see how the left corner of the top of my rectangle is hitting the curve. All right? So that's what left endpoint means. The left side of the rectangle hits the curve. And so for my next interval from 4 thirds to 5 thirds, that base, my rectangle is going to hit the curve on the 4 thirds side. So this will be the height of my second rectangle at 4 thirds. And then I draw a horizontal line over down to my 5 thirds. And I continue the process with the top left corner hitting the curve for every rectangle. All right, so a very badly drawn picture, but hopefully enough to convey the idea. So we have 6 rectangles of equal width, 1/3, in different heights, but the height of each rectangle can match up with the height of the curve at those points on the left side. So now, the idea of, you can see that this, if I add the areas of these rectangles, right, if I add those areas together, then I'm going to be close to the area under the curve, except for these little gaps here that are kind of almost triangular shapes, right? I'll be short of the area under the curve by those little gaps. But I could refine my approximation by doing things like increasing the number of rectangles. If my rectangles are narrower, those gaps become smaller, okay? And that's kind of what integral calculus is all about. So what we're going to do now is actually find the areas of the rectangles and add those together to approximate the area under the curve. And this is where the calculator will come in handy for sure. So here we go. So the area under the curve is approximately equal to, well, I need the area of my first rectangle. The area of my first rectangle is base times height. Well, the base length is 1/3. The height is the same as the y value right here on this curve. So in other words, the height of the first rectangle is the output for 1, meaning it can be calculated by calculating the output of 1 for the function f, which is this guy. Maybe I should label this as f of x equals. So this is our function, f of x. And so the heights of the rectangles now correspond to y values or outputs of that function. Okay? So that's my first rectangle. Then my second rectangle is going to be the base 1/3 times the height at 4/3. And then I just continue the base 1/3 times the height at 5/3. And I keep going, right? I keep going. Let's go ahead and write all of them. There's only 6. Notice that my last height is going to be measured at 8/3, not at 3. I don't have any rectangles that have a height that match to the y value of 3, because that's a right endpoint. So I'm going to continue this process until I have 6 rectangles, and you'll see that the last one ends at the height of 8/3. 6/3 I can put plus 1/3 times f of 7/3 plus 1/3 times f of 8/3, okay? Now, you could certainly type all of this into your calculator by storing that function and then typing all of this at once. That's one way to do it. But what you start to recognize is, because you're working with this constant delta x, this constant width for all your rectangles, you can always factor that width out. So you can factor the 1/3 out, and all that remains is the sum of the heights. And I'm not going to write them all down again. I'll write the first couple and the last couple. But we can see that if I factor out the 1/3, this is what I get. So now I'm going to grab my calculator and I'm going to store this function, as I showed earlier in the video. It should already be there. So what I'm going to do now is type my 1/3 fraction and parentheses, and in my parentheses I'm going to type f of 1 plus f of 2/3 all the way up to plus f of 8/3. You don't need to watch me do that. I'll be right back. Okay, and it looks like we get 163 over 27. So this is an approximation for the area under this curve, this function, from x equals 1 to 3, using 6 rectangles and left endpoints. So pretty simple. You just need to make sure you get your x values, and you understand you never use all of the x values you have listed here, right? If you're using left endpoints, you use all the left endpoints of every interval, so that excludes 3 at the end. If you use right endpoints, which we'll look at next, you're going to start at 4/3 and leave out the 1. So the 4/3 all the way to 3 will be your right endpoints. And then we'll look at midpoints, which are going to use the x values halfway between each of those, okay? Now, the other concept I want to mention here is that this number, since all of these rectangles live underneath the curve, since all the rectangles live underneath the curve, this is an underestimate for the area, okay? So it's kind of nice to know that. It's not always true that if you use rectangles that you can tell if you get an underestimate or an overestimate. Depending on how your curve increases and decreases and is concave up, concave down, your rectangles could go above in some places and stay below in others. So the amount that they're off could sort of cancel each other out a bit. But this is the basic idea for approximating areas under curves. Now, let's change the problem using right endpoints. We're not going to work out the details now because it's the same way every time, but we might as well look at all of this while we're here. So I'll be drawing a new picture now, new rectangles. Since we're using 6 rectangles, the x values at the bottom will stay the same. But now, if we're using right endpoints, I already alluded to it, then all you're going to do is for your first rectangle, you're going to measure the height of that rectangle at not 1, but at 4/3 now. So you're going to come up here like this, and now when you draw your horizontal line, it's going to go over the top of the curve, right? So you can see now that this rectangle is going to be an overestimate of the area under the curve. And if you continue that process, you get the same thing all the way across. So you have 6 rectangles now that supersede the top of the curve, and therefore the approximate area is going to be an overestimate. And so we'll just kind of write it out. If you factor out the common width, 1/3, then what you're left with now for your heights are f of 4/3 all the way up to f of 3. So f of 4/3 plus f of 5/3 plus ... all the way up to f of 8/3 plus f of 3. And you could do that in your calculator. I'm not concerned about the number, but it should be bigger than the 163/27 that we had before. And this is an overestimate, again, since every rectangle goes over the top of the curve. So that's right endpoints now. Let's do one more. Let's get the idea for the midpoint method. The midpoint method can be pretty good. It's a little more work. So when you do your midpoint method, now these x values don't work anymore. So what you have to do now is you have to find the middle of each of those. So I'll erase the x values we had before. I'll leave the tick marks, understanding where they are. And now what we'll do is we'll look at the halfway points. And the previous x values were in thirds. So if we're going to look at halfway points, we better think of sixth. So this is 6 sixths plus 2 more sixths gives us 8 sixths. So the midpoint here now is 7 sixths. And then we've got 8 sixths, and then we've got 9 sixths. Then we've got 10 sixths and 11 sixths. 12 sixths, we're not going to use that, by the way, and 13 sixths. 14 sixths, and then 15 sixths. The width is still 1/3, you see? The width is still 1/3 of each rectangle. So the corresponding midpoints are 1/3 of a unit apart. It's just they start in the middle of that first rectangle, and then you add 1/3 every time, or 2 sixths every time. So the last one's going to be 17 sixths. So now when you go to create your rectangles, the height of the rectangle corresponds to those midpoints. So the first rectangle now, its height is going to be measured, going to be corresponding to 7/6. And on the left side, it's over the top of the curve, but on the right side, it's below the top of the curve. And so for that reason, that might seem like a better approximation than having rectangles that completely go over the top or completely go underneath the curve. And if we were to continue this, my next rectangle's height would correspond to the, let's see, I missed my vertical line. It should correspond to, so I'm still using the red tick marks for the sides of my rectangle because the black tick marks are in the middle of each rectangle. Okay, so my next height corresponds to 9/6, and the sides hit the red tick marks still. Okay, and so on and so forth. Graph paper might have been good, but so you get the idea. You could keep drawing the rectangles, and so in that case we would have an area of approximately, again the width is still 1/3, but now the heights of your rectangles are f of 7/6 plus f of 9/6. I know that reduces. Plus dot dot dot, you could write them all down. And then the last two are 15/6, f of 15/6 plus f of 17/6. So the other thing about using midpoints is you actually use all 6. There are 6 midpoints here, so you use all 6 of those when calculating the heights of your rectangles. Whereas when you use left endpoints, you only use the left side of each interval. And when you use right endpoints, you only use the right side of each interval. Okay? And we can't say here, at this point I don't want to really discuss if this is an overestimate or underestimate because you've got part of each rectangle above and part of each rectangle below, and that's not really the emphasis of this video to talk about which of those is bigger or smaller. But that's the idea for approximating the area under a curve.